So we're going to define some basic thermal terms, define pressure and its variation with depth, and then do a quick example on a manometer. So last class we talked about the zeroth law, the first law, and the second law. What did the zeroth law kind of tell us? Do you remember? Yeah. So basically, if one body is touching another body, eventually there'll be an equilibrium. Yep. First law, what did that say? Yep, conservation of energy. Yep. And trust me, that's really all thermo is. Okay. It's conservation of all different types of energy. All right. And then second law told us what? The direction of heat flow. Correct. Yep. And then we talked about open and closed systems. So, okay. So let's do some thermal properties today. So thermo, this is basically objective one. There's some definitions, and then we'll get into pressure, okay? So property. And if the font's too small, just let me know in the back. That's me. Oh, I'm so looking forward to this class. It's fun. Challenging, that fun. So a property is any characteristic of a system. So it could be pressure, temperature, volume, mass, entropy, enthalpy, whatever. Specific properties. Those are all in terms of per unit mass. So some units, some like pressure and temperature don't really, don't need to divide by mass, okay? There are some terms that we do divide by mass. So this one is specific volume. So the unit would be meters cubed per kilogram. Okay. Anybody want to guess what the middle one is?
Specific energy.
Yeah, specific energy. Yes. Yep. Unit of that would be maybe kilojoules per kilogram. And then this is specific enthalpy. This is usually kilojoules per kilogram. In the back of the book, enthalpy is given for a lot of different specifications. So let's look at a process. Big H is enthalpy, yes, unit of kilojoules, yep. So a process is basically, it goes from one state, which is 1, to another state at equilibrium, okay? And the black, that's just the path that it took. Typically, what we're considered in thermo is from one state to the next. We don't care about the path too much. But we're going to assume that each state is at equilibrium. Oh, that should be 2. Why did I do 1? So this is state 2. All right, so there are 4 different processes. Bless you. that you'll hear a lot during this class. So anybody want to guess one of these, what these mean? ISO is meaning kind of one. Which one? The first one? Isothermal? Yep. But what does that mean about temperature? It's constant. Yes. This is constant T. All right. I'm going to keep guessing. Perfect. Yep. But isometric. Volume. Constant mass, that's always, the conservation of mass is always true on any of these, okay? But yeah, constant V. And this one you probably have never heard, but we'll do a lot of it. P, pressure, times volume raised to this N is a constant. And most of the time, processes are kind of that, but we assume other things. But we'll get to that in more detail later on. Questions so far? So a lot of the times you read a problem, it'll be a rigid container. Anybody want to guess what that process is? It says a rigid container. Isometric, yeah. So rigid container means it's not going to expand or compress, okay? So that would be the assumption, isometric, all right? Yep. Trust me, there's one. I remember one homework problem that throws people off on that. I think I gave a test question too that got everyone too. All right, so for D, it's pressure. So that's a good point. Pressure, I always use capital P. Density is rho. It looks like a funny looking tail. Or a balloon. I never thought of that. Yep, a balloon. I can go with that. And do you remember what I called that variable just like 5 minutes ago? Specific volume, which is what? Big V over. And what does that look like? The inverse of density. Yes. Trust me. Remember that. Okay? We get specific volumes in the back of the book in the tables, and you can invert that to get the density of water or whatever material, okay? Or fluid, I would say, not material. Yeah, so the units are, let me do this in red for you, would be kilograms per meter cubed, and the unit of this would be meters cubed per kilogram. And I'm just going to do temperature here because there's not much on that. So how many scales are there? 4. Yep. So we have degree C, degree F, Kelvin, and Rankine. The two I circled in blue are really the only ones you're ever going to use in your equations because they are absolute values, meaning they never really go below 0 or negative, because you can get negative Celsius and negative Fahrenheit, right? But negative does not work in the ideal gas equation. It may work for you, but it won't be the right answer, okay? Okay, so that was objective 1. So let's get into pressure. So pressure, I'll give you the basic definition first because it's easy. Pressure is force over area, right? Remember that? So pressure is just a force over area. So I think the one homework on your new assignment that I'll post Monday actually calculates and looks at snowshoes. Okay, so this is the reason why you can wear snowshoes, which are bigger, and you can walk on the snow. Okay, basically you have smaller amount of pressure. All right, I think we did that in the fluid section. So basically all it is a force over an area. So that's what pressure is. And what happens is the air molecules in here, they're bouncing around. They're really tiny, but they're bouncing around, and the force at which they hit an object, okay, over the area that they touch, that's what pressure is defined as. Oh, so let me write this. So let's look at gauge pressure. So a lot of the times we'll deal with gauge pressure, which is really just your absolute pressure minus an atmospheric pressure. So when you use your gauge to check your tire gauge, it's actually measuring gauge pressure. Okay, so you'd have to take and add atmospheric to get the total pressure that's inside your car tire. Okay, so sometimes we do this. Sometimes it makes life easier because if your absolute pressure is 14.7 psi and you subtract 14.7, which is atmospheric, you get 0. There's conditions where in actually intermediate fluids where you want to assume gauge pressure because it's 0 and stuff cancels out like crazy. Okay, so sometimes it's easier. That's fine for that. Okay, so let's look at pressure with depth. So this is water. It's like a tank or a riverbed or a lake bed. It doesn't really matter. So PT is the top pressure. And PB is the bottom pressure. Okay. So in a lake, the density of water is a little higher, right, than air. So the pressure actually builds up faster. So that's why you need to wear stuff when you scuba dive. All right. You need to breathe, and you can't go down too far, otherwise your lungs will collapse because it's such a high pressure. So the pressure at the bottom is the pressure at the top plus rho GH. So how do we measure pressure? So we could use a device called the manometer. And what this is, it's a fluid column that moves up and down. So let's do a sketch here. we have these in the lab. If you want to see how one works, I can show you in the lab. So a manometer, basically, this heavy fluid, it could be mercury in this case, moves up and down depending on this PA up top here and this pressure inside here. Okay, so it moves up and down, and we can actually find the actual pressure inside this tank right here by using these equations. All right, so let's find that. So let's find PI. So what we can do is, let me do it in, oops, I did not mean to do that. Close the whole thing. That's the one I need to hit. View full page. So pressure, the cool thing is the pressure at this point right here, where that X is, and this dot right here, because it's the same fluid, is at the same pressure. Okay? So we can find this pressure along this depth. Because this is the same fluid, this pressure right here is at the same, or this point is at the same pressure. Okay? So let's find the pressure at B, which is this interface here between the top of this mercury and the air section. So how would you find that? Yeah. Yep. So it's the pressure at the top plus rho of the mercury times G times H. So as long as it's the same type of fluid and it's at the same elevation, it'll be at the same pressure. All right. So let's find that pressure. 96 kilopascals plus 850 kilograms per meter cubed times 9.81 meters per second squared times 55 centimeters, and we got to convert that. So we get about 100.6 kilopascals. So the pressure at this point and this point is 100.6 kilopascals. Okay? So how do we now find the pressure inside the tank if it's air? Well, we know that the pressure at B is the top pressure. So see this right here? We'll assume that's the top pressure. So PI plus rho of air times G times X. So that X is the distance from the air down. PI. So I'm going to rearrange this and solve for PI. Yeah, it's this inside pressure of that tank. Yep. So PI is 100.6 kilopascals minus, anybody know what the density of the air is? Yeah, really close to it. It's actually 1.176 kilograms per meter cubed times 9.81 meters per second squared times, what did I pick? Let's do 25 centimeters. Can someone put that in their calculator for me? Yeah. Huh. Why? What's the density of air? Really small. It's 1.176, where the density of mercury is 850. Okay. So technically, when you do these problems, if it's air in there, you don't have to do this last step here that we did right here. Okay. Yep. Yep. Yep.